Welcome back to CVMX. Today we're diving into the cutting edge of AI, exploring the most important and unique interview questions on AI agents and agentic AI. Whether you're prepping for a job interview, building next-gen agentic systems, or just obsessed with the future of artificial intelligence, this video is for you. Stay tuned. Let's unlock what it really means to design, build, and evaluate modern AI agents. What is an AI agent, and how does it differ from a traditional AI system? Traditional AI systems are usually built to perform a single task in isolation. For example, a spam filter that classifies emails or a vision model that labels objects in an image. An AI agent, on the other hand, goes beyond prediction. It can perceive its environment, make decisions, and then take actions to achieve a goal. What makes it powerful is the feedback loop. It senses, acts, and then learns from the outcome. So instead of just predicting stock prices, an agent might actually decide when to buy or sell, monitor market changes, and adjust its strategy. The key difference is that traditional AI is task-specific and static, while agents are autonomous, adaptive, and continuously interacting with the real world. Can you explain the sense-think-act loop in AI agents with an example? The sense-think-act loop is the foundation of how agents operate. They first sense the environment by collecting inputs from sensors, APIs, or user interactions. Then they think, meaning they reason about the situation, plan possible actions, and decide what's best to do. Finally, they act, taking an action that changes the environment. This cycle repeats continuously, allowing the agent to adapt as conditions change. A great example is a self-driving car. It senses traffic lights and nearby vehicles, thinks about whether to brake, accelerate, or change lanes, and then acts by controlling the steering and pedals. What makes it powerful is that this loop isn't one time. It runs constantly, so the agent keeps learning and adjusting. What are the different types of agents? Reactive, deliberative, hybrid, BDI. There are four major types. Reactive agents are the simplest. They just respond to inputs directly, with no memory, like a thermostat that turns heat on or off when the temperature changes. Deliberative agents are more advanced because they plan ahead using models of the world. Think of a chess-playing AI that simulates future moves. Hybrid agents combine both. They can react instantly when needed, but also plan long-term strategies, which is why they're common in real-world systems. Then we have BDI agents, belief, desire, intention models, which try to mimic human reasoning. They maintain beliefs about the world, desires as goals, and intentions as commitments to action. For example, a personal AI assistant using BDI might believe your flight is delayed, desire to get you to your destination, and form the intention to rebook you on another flight. Each type has strengths and trade-offs depending on the application. How does an autonomous agent differ from an intelligent assistant? An intelligent assistant is usually reactive. It waits for the user to give commands and then responds. For example, if I ask Alexa to set a reminder or book a ticket, it executes that single request. An autonomous agent, on the other hand, takes initiative. It can monitor goals, act proactively, and keep running in the background without constant human input. Imagine I want to plan a trip. An assistant might book flights when I ask, but an autonomous agent could track ticket prices, automatically rebook if a flight is canceled, adjust my hotel reservations, and even reschedule my meetings. The difference comes down to dependency. Assistants rely on you to drive the interaction, while autonomous agents can act independently to achieve objectives. Explain the role of environments in agent-based systems. The environment is essentially the world in which the agent operates, and it defines the complexity of the problem. It provides the inputs the agent can sense, and it reacts to the agent's actions. The properties of the environment, whether it's static or dynamic, deterministic or probabilistic, fully observable or partially observable, directly affect how the agent needs to be designed. For example, a chessboard is a fully observable, deterministic environment where agents can calculate optimal moves. But the stock market is a partially observable, stochastic environment. Agents don't have full information and outcomes involve uncertainty. In short, the environment isn't just background context. It's what shapes the agent's strategy, behavior, and intelligence. What's the difference between single agent and multi-agent systems? A single agent system is when you have just one intelligent entity trying to achieve its goal in an environment. For example, a Roomba cleaning a living room. It just senses, decides, and acts without needing to coordinate with anyone else. A multi-agent system, on the other hand, has multiple agents working together or sometimes competing. That brings in new challenges like communication, negotiation, and coordination. A good example is a swarm of drones in disaster relief. They divide areas among themselves, avoid collisions, and share updates to cover a region efficiently. The main difference is that single-agent systems are simpler and focused, while multi-agent systems are dynamic, distributed, and can even show emergent behavior that no single agent is programmed with. Can you walk through a real-world example of a multi-agent system in action? One of the best real-world examples is Amazon's warehouse robots. Each robot is technically an agent. It navigates the warehouse floor, picks items, and delivers them. But what makes it powerful is that they don't work in isolation. They communicate to avoid collisions, share pathways, and optimize the overall flow of the warehouse. The system as a whole is far more efficient than if you just had one robot moving things around. Another example is in finance. Multiple trading bots operate simultaneously, some competing and some cooperating, which together shape the dynamics of the stock market. Multi-agent systems show us that when agents interact, the overall system intelligence can exceed the sum of individual parts. How do we measure performance or success of an AI agent? Measuring performance depends on the context, but broadly it comes down to how well the agent achieves its goals. In reinforcement learning, we often measure cumulative rewards. In enterprise systems, it could be KP as like accuracy, efficiency, or cost savings. For a customer service agent, success might mean resolving more tickets with higher satisfaction scores. For an autonomous car, it's about safety, fuel efficiency, and trip time. I'd also add adaptability, how well the agent performs when conditions change unexpectedly. So success isn't just about one metric. It's a combination of goal achievement, efficiency, adaptability, and in human-facing systems, user experience. What's the difference between AI agents and agentic AI? AI agents are intelligent programs that can perceive their environment and act on it, but they're often limited to task-specific goals. Agentic AI takes it further. These are systems that can not only execute tasks, but also plan multi-step strategies, reflect on their own actions, and adjust over time. In other words, they're more autonomous, more proactive, and more self-correcting. For example, an AI agent might help me book a flight if I ask it. An agentic AI, on the other hand, would proactively plan the entire trip, monitor for delays, rebook flights if needed, and optimize around my preferences without me prompting every step. The shift is from being reactive to being proactive and reflective. Why is memory important for conversational agents? Memory is what makes conversations feel human-like rather than robotic. Without memory, every question resets the context, which is frustrating for users. With short-term memory, the agent can keep track of what was said earlier in the same session. Like if I ask about weather today and then say, "What about tomorrow?" It knows what I'm referring to. With long-term memory, the agent can personalize interactions across sessions, remembering that I'm vegetarian or that I prefer morning meetings. That transforms the agent from a Q&A bot into a real assistant. In practical terms, memory builds continuity, personalization, and trust, which are critical if these systems are going to be truly useful. Explain the BDI model, belief, desire, intention, in AI agents. The BDI model is one of the most influential ways to design intelligent agents. It's inspired by human reasoning. Agents hold beliefs about the world, their knowledge or perception of reality. They have desires, which are goals or states they'd like to achieve. And they form intentions, which are the plans or commitments to make those desires a reality. This is powerful because it makes agents not just reactive, but also goal-driven. For example, a digital travel assistant might believe your flight is delayed, desire to still get you to your destination, and then form the intention to rebook your tickets. The BDI model makes agents behave in ways that feel rational and human-like. What are the pros and cons of a rule-based agent versus a learning agent? Rule-based agents are simple, transparent, and predictable. You always know why they did something because it's based on if-then logic. The downside is they don't scale well in complex or changing environments. Learning agents, on the other hand, adapt through data. They can handle dynamic conditions, but they're less explainable and sometimes fail in unpredictable ways. A thermostat is a simple rule-based agent. If temperature is less than 20, turn heat on. A modern smart energy system is a learning agent. It studies your patterns and optimizes heating. The trade-off is between simplicity and control versus adaptability and intelligence. How do agent architectures evolve from symbolic to reactive, to hybrid to agentic? The evolution reflects growing autonomy. Symbolic agents relied on logic and rules, precise but brittle. Reactive agents dropped the logic-heavy approach and focused on quick responses, but they lacked foresight. Then came hybrid agents, which blended the two, fast reactions plus the ability to plan. Now we're moving toward agentic AI, which adds memory, self-reflection, and long-term goal pursuit. Think of it like this. Symbolic systems were calculators. Reactive ones are reflex machines. Hybrid agents are assistants. And agentic AI is a co-pilot that can reason, self-correct, and collaborate. Each step increases flexibility and realism. What role does reinforcement learning play in AI agent design? Reinforcement learning, RL, is key because it lets agents learn from trial and error. Instead of being told the right answer, the agent interacts with the environment, takes actions, and receives feedback in the form of rewards or penalties. Over time, it figures out the best strategy to maximize rewards. That's why it's so important for uncertain, dynamic environments. A robot learning to walk, for example, doesn't get instructions for each step. It experiments, falls, and improves. RL makes agents more adaptive and resilient, and it's at the heart of how they can learn behaviors instead of being explicitly programmed. Compare model-free versus model-based agents. Model-free agents don't try to understand the world. They just map experiences directly to actions, often using reinforcement learning. It's like learning by trial and error without a mental map. Model-based agents do the opposite. They build an internal model of the environment so they can simulate outcomes and plan ahead. Model-free is simpler and useful in very complex settings where modeling everything is impossible, but it's often inefficient. Model-based is more efficient, but requires more upfront design. For instance, a model-free agent might learn to play Atari just by experience, while a chess engine is model-based, simulating many possible moves before acting. Explain the concept of agent environments, fully versus partially observable. In a fully observable environment, the agent has complete information about the state of the world. Chess is the classic example. You can see the whole board at any time. In a partially observable environment, the agent only has partial or noisy information. The stock market or real-world driving are good examples. You never have complete visibility. This matters because it changes the design. In fully observable settings, planning is more straightforward. In partially observable ones, you need probabilistic reasoning or belief states to deal with uncertainty. What's the significance of Markov decision processes, MDPs, in agent systems? MDPs give us the mathematical framework to describe how agents make decisions. They define states, actions, transitions, and rewards, assuming the future depends only on the present, the Markov property. This helps us formalize the problem. What's the best policy for an agent to maximize long-term rewards? For example, in navigation, each location is a state. Moving north or south are actions, and reaching the goal is a reward. With MDPs, you can calculate strategies, compare them, and optimize. They underpin reinforcement learning and much of modern agent theory. How does planning differ from reactivity in agent systems? Planning is about thinking ahead, simulating future outcomes before acting. Reactivity is about immediate response without long-term reasoning. Both have strengths and weaknesses. Planning is powerful for complex tasks, but slow in fast-changing environments. Reactivity is quick but short-sighted. Real systems often blend the two. A delivery robot might have a long-term plan for the route, but still react instantly if someone steps in front of it. Balancing planning with reactivity is critical to making agents both smart and safe. Describe an agent architecture that enables tool use. Example is APIs databases. Modern agent architectures often treat external tools as actions. The reasoning module decides, do I answer from internal knowledge or call an external API? Frameworks like LangChain or AutoGen are built on this principle. For example, if a user asks a research assistant for weather, the agent might recognize it doesn't know and call a weather API. This makes the agent more capable because it can combine reasoning with specialized external systems instead of being limited to what's inside the model. What are the failure modes in agent planning and execution? Failure happens in both planning and action. Agents might overplan and get stuck in analysis paralysis, or plan with bad assumptions if the environment changes. In execution, they can fail from poor sensing, wrong action selection, or miscommunication. A drone might plan the perfect route but fail to execute because of sudden weather. That's why robust design matters: fallback strategies, error handling, and sometimes even self-correction loops. Failures are unavoidable, so resilient agents are designed not just to succeed, but to recover gracefully when things go wrong. How do agents communicate in a multi-agent system? In multi-agent systems, communication is key because agents often need to coordinate, share knowledge, or negotiate tasks. This can happen through direct message passing, where one agent explicitly sends structured data to another, or through indirect communication in the environment, which is called stigmergy, like ants leaving pheromone trails. The protocol depends on the system design. Some use predefined schemas, others even leverage natural language or APIs. A real-world example is autonomous vehicles. Cars exchange information about speed, lane changes, and road hazards to avoid collisions and optimize traffic flow. Without communication, the system would be chaotic. With communication, agents can behave like a team. Explain cooperation versus competition in multi-agent environments. Agents can either cooperate or compete, depending on whether their goals align. In cooperative systems, all agents share a common objective. For example, a swarm of drones searching for survivors after a disaster, each covering a different area. In competitive environments, goals conflict, so agents are rivals, like trading bots trying to outbid one another in the stock market. Many real-world systems are actually a mix of both. For instance, ride-sharing companies may coordinate fleets internally to distribute passengers, but externally they're competing with other providers. The balance between cooperation and competition shapes strategies and outcomes in multi-agent ecosystems. What's the role of coordination protocols? Example is contract net protocol. Coordination protocols help agents assign tasks efficiently and avoid conflicts. A well-known one is the contract net protocol. Here, one agent announces a task, others bid to perform it, and the best-suited agent wins. This is especially useful in distributed environments where no central controller exists. For example, in a warehouse, a robot might broadcast that an item needs moving, and others can bid based on distance or availability. The point of protocols like these is to bring order and efficiency into decentralized systems. Otherwise, agents might duplicate work or interfere with each other. How do agents handle conflict resolution in decision-making? Conflicts are inevitable when multiple agents share resources or have overlapping goals. They're resolved using strategies like negotiation, prioritization rules, or escalation to a higher authority. Sometimes agents compromise, sometimes they yield, and sometimes they escalate. A great example is air traffic control. Planes act as autonomous agents to some extent, but conflicts like potential collisions are resolved through a centralized system giving priority and instructions. In digital systems, this ensures agents don't deadlock or waste resources. Good conflict resolution design ensures smooth collaboration, even in high-stakes environments. What's the difference between distributed AI and multi-agent systems? They sound similar, but there's a key difference. Distributed AI is about splitting computation across multiple nodes to solve a problem faster or at larger scale. Think of cloud computing or MapReduce. Multi-agent systems, on the other hand, treat each node as an intelligent entity with its own goals and decision-making. For example, in energy grids, distributed AI might crunch massive optimization problems across servers, while multi-agent systems might model households as independent agents negotiating when to consume or sell energy. So distributed AI is about computation, while multi-agent systems are about autonomy and interaction. How do you ensure scalability when deploying hundreds of agents? Scalability is one of the toughest challenges. The key is to avoid central bottlenecks and let agents operate in a decentralized way. Techniques include limiting communication to local neighbors instead of global broadcasting, modular designs, and efficient task allocation protocols. For example, in swarm robotics, each robot only communicates with its closest peers, which keeps the system efficient even with thousands of units. In software, cloud platforms and distributed architectures help. The main principle is that the system's complexity should grow linearly or less and with the number of agents, not exponentially. That's how you scale from tens to thousands. Can you give an example of emergent behavior in multi-agent systems? Emergent behavior happens when simple rules at the agent level create unexpected, complex patterns at the system level. In nature, bird flocking or fish schooling are classic examples. Each follows local rules, yet the group moves beautifully in sync. In artificial systems, swarm robotics shows this clearly. Give each robot simple rules for avoiding obstacles and maintaining distance, and together they can cover an area or form shapes without central control. The fascinating part is that no agent is explicitly programmed to create the global behavior. It emerges naturally from their interactions. How do agents share or negotiate knowledge and goals? Agents share knowledge by broadcasting information, exchanging models, or updating shared data structures. Negotiation comes in when goals conflict or resources are limited. This often involves protocols where agents propose, counter-propose, and eventually agree. For example, in a supply chain system, a factory agent, a warehouse agent, and a retailer agent might all negotiate shipping schedules. The factory wants to minimize production cost, the warehouse wants to optimize storage, and the retailer wants timely delivery. Negotiation ensures balance. Whether cooperative or competitive, this exchange is what lets distributed agents align with each other. What are the security risks in multi-agent environments? Security is a serious concern because agents act autonomously and often depend on shared information. Risks include malicious agents spreading false data, denial of service attacks through message flooding, or adversarial manipulation of decisions. There's also the risk of collusion, agents secretly working together against the intended fairness of the system. For example, in financial trading, compromised agents could manipulate prices by creating fake signals. To counter these risks, systems need authentication, monitoring, trust scoring, and sometimes even blockchain-like transparency. Security isn't just a technical issue here, it's fundamental to trust in agent ecosystems. How can blockchain or Web3 enhance trust in agent ecosystems? Blockchain is a natural fit because it provides transparency, immutability, and decentralized trust. Agents can record their transactions on a blockchain so that no single entity can alter history. Smart contracts make it possible for agents to execute agreements automatically, without needing a central authority. For instance, in decentralized energy trading, household agents could negotiate prices and exchange power, with blockchain ensuring fairness in payment. Web3 also enables agents to have unique digital identities, wallets, and reputations. That means trust comes not from a central controller, but from the protocol itself, which is critical when agents interact at scale. What is agentic AI, and how is it different from AI agents? AI agents can perceive their environment, make decisions, and act, but they're often task-specific and reactive. Agentic AI takes that foundation and adds autonomy, memory, and self-reflection. These systems don't just complete isolated tasks. They plan multi-step strategies, monitor progress, self-correct when needed, and even collaborate with other agents. For example, a regular AI agent might book a flight when you ask, but an agentic AI could plan the entire trip, track prices, rebook if there's a delay, adjust hotels, and update your calendar, all proactively. The difference is that AI agents are helpful tools, while agentic AI acts like a proactive collaborator. How does self-reflection improve agentic AI performance? Self-reflection allows the system to evaluate its own outputs and refine them before finalizing. Instead of producing one answer and moving on, it asks, does this look correct? Can I improve it? That creates a feedback loop within the agent itself. For example, if an agent writes code, it can run tests, spot errors, and try again. This leads to higher accuracy and fewer hallucinations. In practice, self-reflection makes agentic AI more reliable because it doesn't rely on first drafts. It critiques and improves its own work, just like a human would proofread or review their thinking before acting. Can you explain recursive prompting and its role in agentic workflows? Recursive prompting is a technique where the agent reuses its own output as the input for further refinement. Instead of a one-shot response, it creates a loop. Generate, review, improve. In agentic workflows, this is critical because it enables self-correction. For example, if an agent generates a draft research summary, it can then reprompt itself with instructions like, make this clearer and more concise, and repeat until the output meets a higher standard. This recursive cycle is how agentic systems move closer to human-like self-improvement. It's the difference between a system that just answers and one that iterates until it gets things right. How do agents use multi-turn memory to sustain long-term goals? Multi-turn memory is what lets agents keep track of context across multiple interactions, instead of treating every request as brand new. Short-term memory maintains flow within a single session, while long-term memory allows persistence across weeks or months. For example, a personal learning agent could remember what topics you struggled with last week and adapt today's lesson accordingly. Without memory, agents reset every time, making them shallow. With memory, they can sustain long-term goals, track progress, and personalize experiences. This is what makes an agent feel more like a companion or co-pilot rather than just a chatbot. What are digital twins in the context of agentic AI? A digital twin is a virtual replica of a real-world system. It mirrors the state, behavior, and dynamics of its counterpart. In agentic AI, digital twins aren't just simulations. They're intelligent entities that can analyze, predict, and optimize. In manufacturing, for example, a factory's digital twin can forecast equipment failures and optimize maintenance schedules. On a personal level, a digital twin of a professional might track their meetings, preferences, and workflows, then simulate decisions to save time. The value of a digital twin in agentic systems is that it allows proactive decision-making before issues arise in the real world. How does goal decomposition work in agentic AI systems? Goal decomposition means breaking a high-level objective into smaller, actionable subtasks. Agentic AI is strong at this because it can reason hierarchically. For example, if the goal is plan a business trip, the system might decompose that into booking flights, reserving hotels, arranging transport, and preparing documents. Each sub-goal can be handled separately, often in parallel, and then stitched together to achieve the bigger goal. This makes vague human instructions workable for machines. Without decomposition, goals would remain too abstract. With it, agents can deliver structured, step-by-step execution, which is what makes them practical in real-world workflows. What role do frameworks like LangChain, Crew AI, and AutoGen play in building agentic AI? These frameworks are the orchestration layer that turns large models into functional agents. On their own, language models can predict text, but frameworks like LangChain, Crew AI, and AutoGen add structure. Memory management, tool integration, multi-agent collaboration, and workflow chaining. For example, LangChain makes it easy to build a research assistant that queries databases, summarizes results, and creates reports. Crew AI specializes in managing teams of agents with different roles. AutoGen supports agent-to-agent conversations for more complex tasks. These frameworks are essential because they provide the scaffolding that bridges raw AI capabilities with usable, agentic applications. How does Model Context Protocol (MCP) enable agent-to-tool integration? MCP acts like a universal adapter between agents and external tools. Instead of coding custom integrations for every service, MCP provides a standardized way to describe available tools and how to use them. The agent can then discover and call those tools dynamically. For instance, if the agent needs weather information, it doesn't hallucinate or require a custom connector. It queries through MCP and gets structured, reliable results. This makes systems more modular, flexible, and scalable because you can plug in new tools without redesigning the whole agent. MCP is a key step toward agent ecosystems that are truly interoperable. Explain the importance of self-correction loops in agentic AI. Self-correction loops are crucial because they bridge the gap between imperfect outputs and reliable performance. No system gets everything right the first time. By embedding a loop where the agent generates an answer, evaluates it, detects issues, and retries, we get much higher reliability. For example, in coding, an agent might write a function, run unit tests, see failures, and then debug itself. This is very different from one-shot systems, which leave errors unresolved. Self-correction turns agents from static responders into resilient problem solvers, capable of improving over time with less human oversight. What are the limitations of current agentic AI systems? While the potential is huge, today's agentic systems have clear limitations. Reliability is still an issue. Agents can hallucinate, miss context, or overcomplicate tasks. Cost and latency are another challenge, since multi-step reasoning often involves multiple expensive model calls. Long-term memory is far from solved. Storing and retrieving knowledge efficiently at scale is still a research challenge. And alignment remains critical, ensuring agents pursue goals exactly as humans intend. Right now, they're more like capable assistants than fully autonomous collaborators. So while the trajectory is exciting, we're still in the early stages of building robust, trustworthy agentic AI. What are the most promising industry applications of agentic AI today? The most exciting opportunities are in industries where tasks are complex and multi-step. In healthcare, agentic systems can summarize patient records, recommend treatments, and even schedule follow-ups. In finance, they can not only analyze data, but also rebalance portfolios and monitor for risks in real time. Customer service is huge. Agents can handle tickets end-to-end instead of just answering FAQs. And in supply chains, agents can coordinate across warehouses, trucks, and retailers to optimize flow. The common thread is that agentic AI doesn't just give answers, it manages processes, acting like a proactive co-pilot rather than a passive tool. How do AI agents enhance customer service automation? Older chatbots were limited to scripted dialogues, but modern AI agents can actually handle full workflows. They can understand intent, fetch data from CRM systems, and take actions like processing refunds or rescheduling deliveries. For example, if a customer reports a damaged order, the agent can confirm the order, initiate a return, arrange a pickup, and send a confirmation email, all without human input. This makes customer service faster, more consistent, and scalable, while freeing human agents to focus on complex or emotional cases. It shifts automation from answering questions to actually resolving problems. What are the challenges of deploying AI agents in enterprises? The challenges are both technical and organizational. On the technical side, integration with legacy systems can be messy. APIs may not exist, or data might be siloed. Reliability is another challenge. Enterprises worry about agents making wrong or costly decisions. On the organizational side, trust and adoption take time. Employees may fear job displacement, and leadership needs clear governance. The best practice is to give agents constrained autonomy with guardrails and escalation protocols. That way, the system adds value without overstepping. So the challenge isn't just building agents, it's making them safe, trusted, and well integrated. How do agentic systems deal with hallucinations in LLMs? Hallucinations are a big issue since LLMs can generate confident but false answers. Agentic systems reduce this by grounding outputs in retrieval augmentation, pulling facts from reliable sources instead of inventing them. They also use self-reflection loops to check and refine outputs, and tool use to fetch data directly from APIs or databases. For instance, if you ask about your bank balance, the agent doesn't guess. It queries the bank's system. By combining reflection, grounding, and external verification, agentic workflows make results more reliable and reduce the risk of hallucination. How do you ensure alignment of agentic AI with human values? Alignment is about making sure agents pursue the right goals in the right way. That starts with designing clear constraints, what the agent can and cannot do. It also means building escalation paths. So when confidence is low or stakes are high, the agent asks for human input. Transparency is important too. The agent should explain its reasoning so humans can trust its choices. And finally, alignment requires monitoring and feedback, continuously testing for bias or harmful behavior. For example, a hiring assistant must enforce fairness and avoid discrimination. Alignment isn't a one-time setup, it's an ongoing governance process. Can you describe an example of AI to AI collaboration in the real world? A good example is software development. One agent might generate code, another reviews it for bugs, and a third runs test cases. Together, they act like a mini-team. Another example is autonomous vehicles. Cars share traffic data with one another in real time, coordinating lane changes or rerouting around accidents. The principle is that specialized agents can collaborate, each playing to their strengths to achieve better outcomes. Instead of one massive agent doing everything, you get a system of cooperating specialists, which is more scalable and efficient. How do you benchmark the performance of agentic systems? Benchmarking is harder than with single AI models because agents perform workflows, not one-off tasks. So you need to measure multiple dimensions: task success rate, efficiency of steps taken, accuracy of tool use, and overall time or cost savings. For customer-facing systems, you'd track metrics like resolution time and satisfaction scores. For research assistants, you'd measure quality and correctness of outputs. Robustness is another key metric. How well does the agent handle unexpected inputs? Emerging benchmarks like Agent Bench are starting to formalize this. Ultimately, success is a mix of quality, reliability, and efficiency. What ethical risks are unique to autonomous AI agents? The unique risk with autonomous agents is that they act independently, sometimes in unexpected ways. For example, a financial trading agent might exploit loopholes in ways that cause harm without breaking rules. There's also the issue of over-delegation, humans trusting agents too much and losing oversight. Accountability is tricky too. If an agent makes a harmful decision, who's responsible? The developer, the company, or the agent itself? These risks are bigger than with static models because autonomy multiplies the impact of errors. That's why guardrails, audits, and accountability structures are critical in agentic deployments. If you were to design a human-AI hybrid agent system, what would it look like? I'd design it so humans focus on strategy, creativity, and judgment, while AI handles data-driven, repetitive, or operational tasks. The AI would act like an intelligent teammate, suggesting options, executing workflows, and surfacing insights. But the human would make final decisions. For example, in healthcare, the AI might analyze test results, suggest diagnoses, and recommend treatments, but the doctor decides and adapts for nuance. The architecture would include shared memory, transparent reasoning, and escalation points. In other words, it's not about replacing humans. It's about combining human strengths with AI efficiency for better outcomes. How does the classical definition of an agent evolve when the core reasoning engine is an LLM? The classical agent, like in Russell and Norvig, is defined by its rationality within a formal PEAS model: performance, environment, actuators, sensors. Its intelligence is explicitly programmed. When you replace the core logic with an LLM, this definition evolves dramatically. The reasoning and world knowledge capabilities are massively enhanced without explicit programming. An LLM agent can handle ambiguity and perform zero-shot planning in ways classical agents cannot. However, a key trade-off emerges. We lose formal rationality and predictability. LLMs are stochastic and can hallucinate, so their actions aren't guaranteed to be optimal. We shift from designing explicit utility functions to guiding a powerful, pre-trained intelligence through careful prompting, grounding, and constraints. It's a move from programmed logic to managed autonomy. Explain the agent environment loop. In a digital agent, what is the environment and what is the hardest part of perception? The agent environment loop is the fundamental cycle of perceive, think, act. The agent perceives its environment, thinks to make a decision, and then acts upon the environment, which creates a new state to perceive. For a digital agent, the environment is its entire digital context: APIs, databases, websites, file systems, or even the user's chat interface. The most challenging part is perception. The environment doesn't provide a clean, structured state. Instead, the agent perceives messy, unstructured data like raw HTML from a website, a complex JSON response from an API, or an ambiguous natural language request from a user. The core challenge of perception is parsing this raw data and grounding it into a meaningful, actionable model of the world that the agent can reason about. Is the belief, desire, intention BDI model still relevant for LLM agents? Absolutely. The BDI model is more relevant than ever, not as a rigid implementation, but as a powerful conceptual framework for designing understandable and predictable LLM agents. We can map its components directly to modern architectures. Beliefs represent the agent's knowledge of the world, which we now implement through its base model knowledge, combined with real-time information from a vector database or RAG. Desires are the high-level goals, which are typically defined by the user's request or the agent's system prompt. Intentions are the concrete, committed plans the agent decides to execute. This is precisely what a chain of thought or React-style reasoning process produces. Using a BDI mindset helps us structure the agent's thinking and ensures it commits to a sensible plan before acting, which is critical for safety and reliability. What is the difference between an agent and a workflow automation or a simple chatbot? The key difference is autonomy and adaptability. A chatbot is primarily reactive. It responds to queries, often by retrieving information, but it doesn't act on that information to achieve a goal. A workflow automation, like Zapier, is purely deterministic. It follows a pre-programmed, rigid sequence of steps, an if-this-then-that logic, and cannot handle any deviation from its script. A system truly becomes an agent when it can independently create and adapt its own plan to achieve a goal. It operates in a dynamic loop. When an action fails or the environment changes unexpectedly, an agent can reason about the failure, replan, and try a different strategy. That ability to make autonomous decisions under uncertainty is the defining threshold. Discuss the concept of situatedness for an AI agent and why it's hard to achieve. Situatedness is the agent's awareness of its specific context, the here and now. It's about understanding its own identity, the current state of its environment, and the immediate history of the interaction. This is incredibly difficult to achieve because LLMs are inherently stateless and trained on a static dataset. They have no built-in concept of time or their immediate digital surroundings. We approximate situatedness using architectural patterns. The three most important are: 1. Dynamic context injection. We constantly feed real-time information, like the current time or API status, into the prompt. Second, stateful memory. We use a short-term memory or scratchpad to maintain the context of the current conversation. 3. Environment querying tools. We give the agent specific tools to actively ask questions about its environment, like a get current system state function, allowing it to perceive its context on demand. Compare a deliberative agent with a reactive agent. When would you choose one over the other? A reactive agent acts on predefined stimulus-response rules, like an if-then statement. It's fast, reliable, and low cost, but it can't handle novel situations. In contrast, a deliberative agent has a world model and explicitly plans a sequence of actions to achieve a goal. It's more intelligent and adaptable, but slower and more computationally expensive. For a commercial application, the choice depends on the task complexity and the need for safety. I would choose a reactive design for high-frequency, low-risk tasks like basic customer support routing or simple data validation. For complex, multi-step tasks requiring problem-solving, like financial analysis or travel planning, a deliberative architecture is necessary. The best systems often blend both, using reactive handlers for common, simple requests and escalating to a deliberative core for more complex problems. Describe a scenario where the React framework would likely fail and how you would augment it. The React Reason Act framework excels at linear, step-by-step tasks. However, it would likely fail in a scenario requiring complex planning with backtracking or exploration of multiple parallel paths. For example, imagine an agent trying to find the cheapest flight combination by checking 3 different travel APIs. If the first API returns no results, a simple React loop might get stuck or give up. It lacks the ability to say, okay, that path failed. Let's backtrack and try the second API from the start, and then compare its results to the third. To augment this, I would implement a tree of thoughts or a graph-based planning module on top of React. This allows the agent to maintain multiple potential plans or thoughts in parallel. It can explore one path, evaluate its success, and if it fails, it can prune that branch and deliberately switch to another promising path instead of getting stuck. Explain a hierarchical agent system and why it's useful for complex tasks. A hierarchical agent system, or a team of agents, is a design pattern where a high-level manager or orchestrator agent decomposes a complex goal into smaller subtasks. It then delegates these subtasks to specialized worker agents. This pattern is incredibly useful for complexity and scalability. For instance, in a marketing campaign agent, the manager agent would break the goal into analyze audience, draft copy, and design visuals. It would then pass these tasks to a data analyst agent, a copywriter agent, and an image generation agent, respectively. The primary challenge is coordination and communication. You need a robust message bus or shared state mechanism for the agents to exchange information and for the manager to synthesize their individual results into a coherent final output. It prevents a single agent from becoming overwhelmed and allows for specialization. When designing an agent's memory, what are the trade-offs between a short-term scratchpad, a long-term vector DB, and a structured DB? The choice of memory system is a critical trade-off between speed, structure, and semantic capability. 1. A short-term scratchpad, which is just part of the context window, is the fastest and is essential for immediate task execution and reasoning. However, it's volatile and has a very limited capacity. 2. A long-term vector database provides semantic memory. It's perfect for retrieving relevant experiences or knowledge based on conceptual similarity, enabling the agent to learn from the past. The trade-off is the cost and latency of retrieval and the risk of retrieving irrelevant information. 3. A structured database like SQL provides perfect factual recall for information with a clear schema, like user profiles or product inventory. It's highly reliable but completely inflexible for unstructured or novel queries. A robust agent almost always needs a hybrid approach, a scratchpad for the now, a vector DB for what have I learned, and a structured DB for what are the facts. To make an agent learn, would you fine-tune the LLM, use RLHF, or use a case-based reasoning module? Justify your choice. For most practical business applications, I would start with a case-based reasoning module implemented via a vector database. Here's my justification. Fine-tuning an LLM is expensive, requires a massive data set of high-quality examples, and risks catastrophic forgetting. RLHF is even more complex, requiring a sophisticated human feedback pipeline and significant compute resources to get right. Both are heavyweight options. In contrast, a case-based reasoning approach is far more agile and scalable. By saving successful and unsuccessful task completions as exemplars in a vector database, the agent can retrieve similar past cases to inform its current plan. This in-context learning is cheaper, more auditable, and allows the agent to improve its performance in near real time as new examples are added without the risks of modifying the base model. How would you design an agent that can dynamically decide which tool to use without being explicitly prompted? The key is to treat tool selection as a reasoning task for the LLM itself. Instead of hard-coding if-then logic, you provide the agent's context prompt with a list of available tools, each with a concise, high-quality description of what it does, its inputs, and its outputs, much like a docstring. When the agent needs to act, it reasons over these descriptions. Its thought process would be to identify the best tool that matches the current subtask. For this to work reliably, the descriptions are critical. They must be unambiguous and clearly state the tool's purpose. I would also implement a default fallback tool or an error handling mechanism for cases where the LLM can't confidently select a tool, preventing it from failing silently. Discuss the trade-offs between an agent using a single, massive LLM versus a mixture of smaller, specialized models. This is a classic performance versus cost trade-off. A single massive model like GPT-4 offers maximum capability and simplifies the architecture. The same powerful brain does everything. The downside is high cost and high latency for every single task, even simple ones. A mixture of smaller, specialized models is far more efficient and scalable. You can use a tiny fast model for simple tasks like intent classification, a mid-size model for basic tool use, and only call the expensive, large model for complex reasoning. This is a mixture of experts approach. The trade-off is increased architectural complexity. You now need a router or an initial classification step to direct the query to the correct model. For a production system at scale, this complexity is almost always worth the significant cost and speed benefits. How does chain of thought prompting evolve into a full-fledged agentic planning mechanism like tree of thoughts? Chain of thought is the foundation. It taught us that getting an LLM to think step by step produces better results. However, it's a linear process. If it makes a mistake early on, the entire plan fails. The evolution to tree of thoughts, TOT, turns this linear chain into a branching exploration. Instead of generating just one next step, the agent generates several potential next steps. It then evaluates these branches, keeps the most promising ones, and prunes the bad ones. This allows the agent to backtrack from mistakes and explore multiple solutions in parallel. It transforms a simple monologue into a structured internal brainstorming session, making the agent a much more robust and flexible planner. What are the primary security risks of granting an AI agent API access, and how would you design a secure sandbox? The two primary risks are unauthorized access and prompt injection. Unauthorized access is the agent being tricked into using its tools on data it shouldn't, like deleting the wrong file. Prompt injection is a malicious user crafting an input that hijacks the agent's instructions, causing it to execute unintended commands. To mitigate this, I would design a secure permission layer that sits between the agent's reasoning core and the tool execution. This sandbox would enforce three rules. 1. Strict validation. It validates every parameter of every API call against a predefined schema. 2. Scoped permissions. The agent's credentials would be tightly scoped, so it can only modify resources it owns. 3. Human in the loop. For any high-risk action, like deletion or sending a large payment, the sandbox would require human confirmation before execution. How would you implement a goal decomposition module to break a complex goal down into executable steps? I would implement this as a recursive planning loop. The planner module receives the high-level goal, like plan a marketing campaign. First, it prompts the LLM with a goal and the list of available tools, asking it to produce a sequence of smaller, high-level steps. For example, 1. Research target audience. 2. Draft ad copy. Then the module iterates through this new plan. For each step, it checks if there is a direct tool that can execute it. If not, it treats that step as a new, smaller goal and calls itself recursively. This process continues until the entire plan consists of concrete, tool-executable actions. The key is defining a clear stopping condition to prevent infinite loops. How can an agent recover from a failed action? Describe a robust error handling and replanning strategy. A robust error handling strategy has three phases: catch, reflect, and replan. First, catch. Every tool execution must be wrapped in a try-except block. This is crucial to catch API failures, timeouts, or invalid outputs without crashing the agent. 2. Reflect. The specific error message from the failed tool is not discarded. Instead, it's fed back into the agent's short-term memory or scratchpad. This makes the agent aware of what went wrong and why. 3rd, replan. The agent is then prompted again with the original goal, the failed plan, and the new context of the error. You explicitly ask it, your previous action failed with this error. Generate a new plan to achieve the goal. This creates a self-correcting loop, allowing the agent to try an alternative tool or approach. What is the role of self-reflection or self-critique in an agent's reasoning loop? The role of self-critique is to significantly improve the quality and reliability of the agent's output. A standard agent generates a plan and executes it. An agent with self-reflection implements a two-step draft and revise process. First, the agent generates an initial plan or response, the draft. Then, before executing it, the agent calls a separate critic module. This module prompts the LLM to review the draft against the original goal, looking for logical flaws, inefficiencies, or potential errors. This critique is then added to the context, and the agent is asked to generate a final, improved version. It's a powerful way to catch mistakes before they happen and is a key step towards more robust autonomous systems. If an agent has access to both a structured SQL database and an unstructured knowledge base via RAG, how would you design a query planner? I would design a router or meta tool as the query planner. This planner's first job is not to answer the query, but to decide which data source is best suited to answer it. When a user query arrives, it's sent to the planner. The planner's prompt includes the user query, the schema of the SQL database, and a description of the types of documents in the vector store. The prompt then asks the LLM to choose between SQL or RAG and to formulate the appropriate query for its chosen source. This ensures that factual, structured queries go to the database, while conceptual, semantic queries go to the RAG system, making the best use of both. In a multi-agent system, what is the difference between cooperation and coordination? They sound similar but are fundamentally different. Cooperation is about shared goals. Agents are cooperative if they work together to achieve a common objective, where success is mutually beneficial. Think of two agents collaborating to write a single report. Coordination is about managing shared resources or dependencies, even if the agents have completely independent goals. It's about deconfliction. Think of two agents in a warehouse. One is stocking shelves and the other is retrieving packages. They don't share a goal, but they must coordinate their movements in the aisles to avoid crashing into each other. You can have coordination without cooperation, and vice versa. Describe the contract net protocol. When would it be an effective mechanism for task allocation? The contract net protocol is a decentralized method for assigning tasks in a multi-agent system, mimicking a real-world bidding process. An agent with a task, the manager, broadcasts a call for proposals to the network. Other agents, the bidders, listen for these calls. If they have the capability to perform the task, they evaluate it and submit a bid. The manager agent then collects these bids and awards the task contract to the most suitable agent based on criteria like speed, cost, or capability. This protocol is most effective in dynamic environments where the best agent for a job isn't known in advance or where agent availability changes over time. It's great for load balancing and leveraging specialized skills within a heterogeneous team of agents. How would you evaluate the performance of an autonomous agent, especially when the correct answer isn't a single string? Evaluating an autonomous agent requires a multifaceted approach that goes beyond simple accuracy. I would implement a three-tier evaluation framework. 1. Task success rate. For tasks with clear outcomes, like, did the user's file get uploaded? We can measure the binary success rate. This is the most important metric. 2. Outcome quality score. For more subjective tasks like summarize this meeting, we can't use string matching. Instead, we use a rubric and either human evaluators or a powerful LLM like GPT-4 as an evaluator agent to score the output's quality, relevance, and coherence on a scale of 1 to 5. 3. Efficiency metrics. Finally, we must track resource consumption. This includes the total tokens used, the number of tool calls, and the end-to-end latency. A successful agent is not just correct, it's also efficient. What is agent drift? And what is the best way to monitor and mitigate it? Agent drift is the degradation of an agent's performance over time, even when its own code hasn't changed. It's caused by shifts in the external environment. An API changes its schema, a website updates its HTML layout, or the underlying data distribution shifts. The best way to combat this is with a continuous evaluation pipeline. I would create a golden data set of representative tasks and run the agent against them on a regular schedule, perhaps nightly. The pipeline would monitor key metrics like success rate and resource usage. If these metrics drop below a certain threshold, it automatically triggers an alert, notifying the development team that the agent's interaction with its environment is broken and needs to be updated. What are the key components of an observability stack for an AI agent? Observability for an agent is about understanding its reasoning process, not just its final output. A good stack must capture the entire thought, action, observation loop. The key components are 1. Trace logging. We need a system, like Langsmith or a custom solution, that logs the full trace of each run, every prompt, every completion, every tool call, and every tool output. This is the foundation for debugging. 2. Metrics. Monitoring. We need to extract and aggregate key metrics from these traces. The frequency of specific tool usage, the error rate per tool, the average number of steps per task, and token consumption. 2. Alerting. Finally, we need an alerting layer that triggers on anomalies in these metrics, such as a sudden spike in failed API calls or an agent entering an abnormally long reasoning loop. Describe 2 different design patterns for implementing human-in-the-loop to HETL verification. The 2 primary HETL patterns are confirmation and correction. First, confirmation is used for high-stakes actions. The agent completes its reasoning and proposes a final plan, like API call, transfer funds, amount equals 500. Before executing, the system pauses and presents this plan to a human for a simple approve or deny. This is a critical safety gate. Second, correction is used when the agent is uncertain or fails. If the agent can't parse a user's ambiguous request or a tool call repeatedly fails, it shouldn't get stuck in a loop. Instead, it should escalate to a human, presenting its current context and asking for clarification or guidance. This turns failures into opportunities for learning. What are the most important ethical guardrails to build around an agent with access to real-world tools? Beyond the standard content moderation of the LLM itself, there are 3 agent-specific guardrails that are non-negotiable. 1. Strict scope limitation. The agent must operate under the principle of least privilege. It should only be granted API keys and permissions for the absolute minimum set of tools required for its function. 2. Deterministic pre-filtering. Before the agent's powerful but unpredictable LLM brain is even invoked, we should use a simpler, faster, and more deterministic model or a set of rules to check the user's intent. This can block obviously malicious or out-of-scope requests early. 3. Immutable audit trails. Every single thought and action the agent takes must be logged immutably. In the event of a failure or a malicious action, we need a complete, unalterable record of its decision-making process for forensic analysis and accountability. When would you use a framework like LangChain versus building an agent from scratch with a library like Boto 3 or requests? The choice depends on the project's maturity. LangChain is exceptional for speed and prototyping. Its abstractions and vast library of integrations allow you to build a proof of concept in hours, not weeks. It's the best choice for exploring a new idea. However, for a production system, I would lean towards building the core agent loop from scratch. This gives you maximum control over the prompts, better performance, and complete transparency for debugging. You avoid the magic of a framework's abstractions, which can be difficult to manage when you need fine-grained optimization and reliability. The ideal path is often to prototype in LangChain, identify what works, and then refactor the core logic for production. Explain the difference between prompt chaining and an agent loop. The difference is between a static and a dynamic workflow. Prompt chaining is a fixed, linear sequence of steps. The output of prompt A is always fed into prompt B, which is always fed into prompt C. It's a deterministic pipeline, ideal for predictable tasks like document summarization, followed by sentiment analysis. An agent loop is a dynamic, cyclical process. The output of a step is used to decide the next step. The agent might call a tool, get an observation, and based on that result, it could decide to call another tool, ask the user a question, or conclude its task. It's adaptive and essential for any task that involves problem-solving in an unpredictable environment. How do you manage state for an agent when LLMs are inherently stateless? You're right, the LLM itself has no memory, so we have to build state management around it. There are three common patterns. One, in-context state. This is the simplest form where the state, like conversation history or scratchpad notes, is passed directly into the context window on every call. It's fast but limited by the context window size. Two, database state. For long-term persistence, we use an external database. This could be a simple key value store like Redis for session information or a SQL database for structured user data. The agent is given tools to read and write to this database. Three, file system state. For complex tasks that produce artifacts, like writing code or reports, the agent can be given tools to read and write to a local or cloud file system. This allows it to manage state in a way that's persistent and easily accessible to other processes. What is the practical difference between a model with native function calling and an agent using a React prompting style? The practical difference is reliability and structure. A React agent uses a general-purpose text completion model. We teach it through prompting to generate text in a specific format, like action search Josh API of query, which our code then has to parse. This is clever, but can be brittle. If the model deviates from the format, the parsing fails. A model with native function calling has been specifically fine-tuned to recognize when a tool is needed and to output a structured JSON object describing that tool call. This is far more reliable because we're no longer parsing unstructured text. We're just consuming a predictable JSON output. It's a more robust and production-ready way to implement tool use. How would you unit test a non-deterministic AI agent? You can't truly unit test the non-deterministic LLM core, but you can and must test everything around it. My strategy would be three-layered. One, unit test the tools. Each tool the agent can call, like an API wrapper, is a deterministic piece of code. These should be unit tested rigorously with mocked inputs and expected outputs. Two, integration. Test the logic. I would test the agent's data handling and state management logic. For example, I'd verify that after a mock tool call, the agent's scratchpad is updated correctly. Three, create evals for the core. For the LLM's reasoning, we create an evaluation set of input prompts and their desired outcomes. We can't assert an exact string match, but we can write logic to check if the final output meets certain criteria. For example, does the output contain a valid JSON object? Or is the sentiment of the summary positive? This provides a benchmark for the agent's performance. What does embodiment mean for a purely digital agent? And why is it a useful concept? For a physical robot, embodiment is obvious, it's the robot's body. For a digital agent, embodiment refers to its persistent presence and set of capabilities within its digital environment. It's the sum of its tools, its permissions, its identity, like an API key, and its ability to perceive and act upon that environment. This concept is useful because it forces us to think beyond the brain in a vat. An agent's intelligence isn't just in the LLM, it's in the interaction between the LLM's reasoning and the specific digital body it's given. A powerful LLM with no tools is useless. A simple LLM with a rich set of tools can be incredibly effective. Embodiment frames the design problem as building the right body for the brain. Discuss the challenges an LLM agent faces with long-term planning and potential solutions. LLM agents struggle with long-term planning primarily due to their limited context windows and lack of persistent memory. They can't keep the whole plan in their head for a multi-week project. They suffer from context drift and can easily lose track of the high-level goal. The most promising solution is a hierarchical architecture combined with a persistent memory store. A high-level planner agent would create an initial project outline and save it to a database. Then, on a daily or hourly basis, a lower-level worker agent is activated. Its prompt would be populated with only the main goal and the specific next task from the database. This worker completes its task, updates the project state in the database, and shuts down, effectively managing state externally. How could you design an agent with intrinsic motivation to explore or learn without explicit instructions? This is a frontier research area, but a practical approach is to implement a curiosity-driven learning loop. You would give the agent a set of core tools and a meta tool called Learn New Skill. The agent's core directive would not be to solve a specific task, but to minimize its own uncertainty. You would run simulations where the agent encounters problems. If it fails to solve a problem, the failure itself becomes a trigger. The agent is then prompted with, "You failed at this task. Formulate a hypothesis about a new tool that could have helped you succeed." Its output could be a Python function signature, which is then passed to another LLM to generate the code. This creates a cycle where failure drives exploration and skill acquisition. Why is causal reasoning difficult for LLMs? And how does this impact an agent's planning? LLMs are masters of correlation, not causation. They are trained on static text to predict the next word, so they learn strong associations between concepts. However, they don't have a true underlying model of cause and effect. This severely impacts an agent's ability to plan in novel situations. An agent might know that low stock and place order are correlated, but it doesn't understand that low stock causes the need to place an order. This means it can easily fail when the environment changes. If a new policy is introduced where orders are placed automatically, a human understands the causal link is broken, but the agent might keep trying to place orders, leading to errors. Overcoming this requires integrating symbolic causal models with the LLM's reasoning. How can an agent apply knowledge from one task, booking a flight, to a new task, booking a train? This is about generalization, and it's a key strength of LLM-based agents. The agent achieves this not by transferring code, but by transferring the abstract reasoning pattern. The agent's memory of booking a flight would look like goal, travel, steps, identify departure, arrival, search for options, select a time, provide payment. When faced with booking a train, the LLM recognizes the high-level semantic similarity of the goal. It retrieves the flight booking plan from its memory and uses it as a template. It hypothesizes that it will need to follow a similar pattern, but it intelligently substitutes the specific tool from search flights to search trains. It's learning the how, not the what. Explain the difference between symbolic and subsymbolic reasoning. Why is a hybrid approach powerful? Subsymbolic reasoning is the intuitive, pattern-matching intelligence of the LLM's neural network. It's powerful for understanding natural language and handling ambiguity. Symbolic reasoning is the explicit, logical world of knowledge graphs, databases, and mathematical equations. It's precise, verifiable, and excellent for facts. A hybrid approach is powerful because it combines the strengths of both. The LLM acts as a brilliant translator between the user's messy, ambiguous request and the rigid, structured world of symbolic tools. It can parse a vague question, formulate a precise SQL query, symbolic, execute it, get a factual result, and then translate that result back into a natural, easy-to-understand answer, subsymbolic. What can modern agent designers learn from older cognitive architectures like SOAR or ACTAR? We can learn a tremendous amount about structure and memory. While LLMs provide a revolutionary reasoning engine, these older architectures were deeply focused on the scaffolding around the reasoner. For example, SOAR is built on the problem space hypothesis and the universal weak method. This teaches us the importance of explicitly defining the agent's goals, operators, and state. ACT-R has highly detailed models of different memory systems, like declarative and procedural memory. This reminds us that a simple vector database is not enough. A robust agent needs multiple specialized memory systems to truly learn and adapt. They provide a blueprint for the components we need to build around the element. How does the AI alignment problem manifest in an autonomous agent with tool use capabilities? In a simple chatbot, alignment is about not generating harmful content. For an agent, the problem becomes much more severe. It's about preventing harmful actions. The problem manifests in two ways. First is goal misinterpretation. The agent pursues the stated goal literally, without accounting for implicit human values, leading to negative side effects, the classic paperclip maximizer problem. Second is instrumental goals. To achieve its primary goal, The agent might decide it needs to acquire more resources or bypass safety constraints, viewing them as obstacles. An agent with tool use is no longer just a text generator. It's an actor in the world, making the consequences of misalignment far more direct and dangerous. Where do you see agent frameworks evolving? What is the next big thing in agent architecture? Current frameworks are excellent for chaining tools together. The next evolution is towards multi-agent collaboration and stateful, long-running processes. Frameworks will move from managing single-shot tasks to orchestrating teams of specialized agents that can work on complex projects over days or weeks. The next big thing in architecture will be the standardization of the agent operating system. This will be a more integrated platform that provides core, shared services for agents, like persistent memory, secure credential management, inter-agent communication buses, and continuous evaluation, allowing developers to focus on the agent's unique skills rather than rebuilding this complex infrastructure every time. Is the agent environment loop a sufficient paradigm for AGI, or is a fundamental component missing? The agent environment loop is a powerful and necessary paradigm, but I believe it's insufficient on its own for AGI. It excellently models reactive and deliberative intelligence, but it's missing a key component: self-directed growth and curriculum generation. Current agents are largely passive. They learn by being given tasks. A true AGI would need an intrinsic drive, a form of computational curiosity that motivates it to explore its environment, identify its own knowledge gaps, and create its own curriculum to learn new skills without external prompting. The missing piece isn't just a better reasoner or more memory. It's the internal spark that drives self-directed evolution. You need to build an agent to automate a business process. What are the first three questions you ask the stakeholders? My first three questions are focused on value, feasibility, and safety. 1. What is the single most valuable, measurable outcome of this process? This forces a clear definition of success. Is it reduced call time, increased sales conversion, or fewer errors? Without a clear KPI, we can't measure ROI. 2. Where does the process require subjective judgment versus following deterministic rules? This helps me identify which parts are ripe for automation with today's technology, rules-based parts, and which will require more complex reasoning or a human-in-the-loop, judgment-based parts. 3. What is the cost of failure at each step? This is the risk assessment. It tells me where to build in the most robust error handling and where to require mandatory human oversight, ensuring we build a system that is not only effective but also safe and reliable. How do you decide between building a single, monolithic agent versus a team of smaller, specialized agents? The decision hinges on the complexity and divisibility of the workflow. I would choose a monolithic agent for a linear, single-domain task, like an agent that only processes customer support tickets. The entire context is self-contained, and there's no benefit to splitting it up. I would choose a team of specialized agents for any complex, multi-domain workflow. For example, an e-commerce management system. It's far more robust and scalable to have a customer support agent, an inventory agent, and a marketing agent. They can work in parallel, be updated independently, and the cognitive load on each agent is much lower. The orchestrator manages the workflow, but the specialists do the work. This mirrors a well-run human organization. Describe a kill switch mechanism for an autonomous agent. Why is it more complex than just stopping a process? A kill switch is an essential safety feature, and it's complex because a safe state isn't just about stopping. A robust kill switch has three components. 1. Graceful shutdown. The switch shouldn't just terminate the process, which could leave databases in a corrupt state or half-finished API calls. It must first signal the agent to cancel in-flight operations and stop accepting new tasks. Second, state reversion. For critical operations, the agent should be designed to support transactions. The kill switch should trigger a rollback to the last known good state, preventing partial or erroneous changes. Third, post-mortem logging. When the switch is activated, the agent must immediately log its entire current state, its memory, its last few actions, and the reason for the shutdown to a secure location. This is critical for debugging what went wrong and ensuring it doesn't happen again. What is token stuffing, and how can you engineer your prompts to avoid it and reduce costs? Token stuffing is the inefficient practice of filling an agent's context window with large, irrelevant blocks of text, like entire documents or excessively long conversation histories. This dramatically increases costs and can actually reduce performance by burying the important information in noise. To avoid it, I use two techniques. One, summarization. Instead of passing the full conversation history, I use a cheap, fast model to create a running summary of the conversation and pass that into the prompt of the more expensive model. Two, retrieval augmented generation, your RAG. Instead of stuffing a whole document into the context, I place it in a vector database. The agent first performs a semantic search to retrieve only the 2 to 3 most relevant chunks of information and places only those into its context. This is far cheaper and more effective. How would you design an A/B testing framework for an AI agent to prove its business value? I would design the A/B test around the key business metric we're trying to improve. For example, if it's a customer support agent, the metric is customer satisfaction score, or time to resolution. The framework would randomly route a percentage of incoming requests, say 20%, to the new agent, the challenger. The remaining 80% would be handled by the existing system, the champion. It's crucial that we track the core metric for both groups, as well as secondary guardrail metrics like the escalation rate to a human. The test would run until we have statistical significance, allowing us to prove definitively whether the agent is providing a measurable lift to the business. What are the challenges of managing an agent that interacts with constantly changing web UIs? This is a problem of brittleness. An agent trained to click a button based on its CSS selector will break the moment a developer changes that selector. The solution is to move from syntactic to semantic interaction. Instead of telling the agent to click button number submit V2, we give it a more abstract goal, like click the confirm order button next to the total price. The agent then uses a vision-capable model to look at a screenshot of the page, locate the button that semantically matches that description, and then programmatically clicks it. This makes the agent resilient to minor UI changes and is a key step towards more robust web automation. Explain the concept of a shared tool library in a multi-agent system. A shared tool library is a centralized, version-controlled repository of the tools available to all agents in a system. Instead of each agent having its own hard-coded set of tools, they all reference this common library. This has 3 huge benefits for production systems. 1. Consistency. All agents use the exact same implementation of a tool, preventing weird, hard-to-debug inconsistencies. Second, reusability. A developer can write and test a tool once, like a Salesforce API wrapper, and it can be immediately used by any agent that needs it. 3. Maintainability. If an API changes, you only have to update it in one place, the shared library, and all the agents that use it are instantly updated. It's a foundational practice for scalable agent development. How does the cost of planning affect an agent's design? When is it better for an agent to just act? The cost of planning refers to the tokens, latency, and compute required for an agent to think through a complex problem. In some cases, this cost can be higher than the cost of making a small mistake. It's better for an agent to just act in low-risk, reversible situations. For example, if an agent is navigating a website, it's often cheaper to just try clicking a link and see what happens than it is to spend 5 seconds and 2,000 tokens reasoning about whether it's the perfect link. If the click is wrong, the cost is a single, reversible back action. The key is to build a system that can tolerate and learn from these small, inexpensive failures, reserving deep planning for high-stakes, irreversible actions. What is the scaffolding around an LLM, and why is it often more important than the choice of the model itself? The scaffolding is all the infrastructure that turns a raw LLM into a reliable agent. This includes the tool library, the memory systems, the error handling and retry logic, the observability stack, and the human-in-the-loop escalation pass. This scaffolding is often more important than the model Because most business tasks don't require a frontier model. They require reliability. A system with a cheaper, faster model, but with robust error handling, great tools, and a solid evaluation pipeline will consistently outperform a system that just uses a powerful model with no support structure. The scaffolding is what makes the agent's intelligence useful and safe in the real world. Looking 5 years into the future, what capability do you believe will be the defining feature of the most advanced AI agents? Looking 5 years out, I believe the defining feature will be proactive goal setting and autonomous learning. Today's agents are fundamentally reactive. They wait for a human to give them a task. The next generation of agents will be proactive. They will be given a high-level mandate, like optimize this company's marketing spend. The agent itself will monitor the data, identify opportunities, propose its own projects, run experiments, and learn from the results without daily human intervention. They will transition from being tools we direct to becoming true autonomous partners that drive outcomes. How do you define an AI agent beyond the textbook sense of perceive plus act? An AI agent, in my view, is an autonomous system that does much more than simple perception and reaction. It actively sets goals, reasons about the world, adapts its strategies, leverages both memory and feedback, and can learn in real time. Effective agents construct internal models, handle ambiguity, and often work collaboratively, interacting with humans or other agents as part of complex systems. This richer concept of agency is what enables AI to solve nuanced and evolving real-world challenges, rather than just responding to predefined triggers. In what ways are AI agents different from traditional rule-based agents in classic AI? Classic rule-based agents are confined to executing rigid if-then logic, which makes them fragile and ill-suited to dynamic environments. AI agents, by contrast, incorporate learning and reasoning, leveraging machine learning, neural networks, or even LLMs, so they can generalize from experience, infer patterns, adapt on the fly, and acquire new capabilities. They are context-aware, deal effectively with uncertainty, and can process unstructured as well as structured data sources, greatly expanding their usefulness and operational resilience. What are the main components of an AI agent architecture? A robust AI agent typically includes a perception module to sense its environment, a state representation to store context and memory, and a policy or decision-making engine to drive actions. Added to that, there are actuators for implementing decisions, a learning module for continuous improvement, and both short-term and long-term memory for context building. In collaborative or multi-agent scenarios, a communication interface is vital, ensuring the agent can coordinate or negotiate with other entities efficiently and transparently. What role does autonomy play in agent design, and how do you measure true autonomy? Autonomy is central to distinguishing intelligent agents from conventional software or automation. It refers to the agent's ability to function independently, making decisions, setting sub-goals, adapting methods, and recovering from unexpected situations. True autonomy becomes evident when the agent can generalize solutions, learn from outcomes, overcome unforeseen obstacles, and pursue high-level objectives in unstructured or novel environments, all while minimizing the need for human oversight or rigid pre-programmed intervention. Can an LLM itself be considered an agent, or is orchestration needed for agency? Argue both sides. On one hand, an LLM can simulate some forms of agency reasoning through prompts, using plugins, and dynamically responding to context. However, truly agentic behavior needs persistent memory, iterative planning, goal setting, and long-term context management, which core LLMs do not natively provide. Therefore, an orchestration layer managing state, history, planning, and tool selection is generally necessary to elevate LLMs from sophisticated responders to fully fledged, persistent agents with enduring objectives and adaptive workflows. Compare BDI models with modern LLM-based agentic architectures. BDI models emphasize explicit reasoning. They manage what the agent knows, wants, and intends to do, making decision flows transparent but often inflexible. Modern LLM-based agentic architectures use large-scale learned associations and chain-of-thought reasoning, enabling richer language understanding and adaptability, but with reduced explainability. Many advanced systems today blend these approaches, layering LLMs for creativity atop structured BDI-like planning in order to combine interpretability and robust behavior in unfamiliar situations. What is an orchestration layer in multi-agent systems, and why is it critical? The orchestration layer acts as the organizing backbone of multi-agent systems, akin to a project manager. It sequences tasks, resolves resource conflicts, mediates communication, tracks progress, and integrates APIs or external tools. This layer is critical for scaling up, coordinating multiple agents, avoiding workflow overlap, ensuring alignment with overarching goals, and maintaining system-wide efficiency. Without orchestration, agents risk chaos, duplicated actions, and unresolved dependencies, which can derail processes or reduce reliability. How would you integrate tool use capabilities, like APIs, calculators, vector stores, into an agent? To effectively integrate tool use, I'd implement an explicit tool interface and equip the agent with meta-reasoning capacities, enabling it to identify the need for a tool, select the best one, and invoke it via modular API calls or plugins. Returned outputs are merged into the agent's memory or context for validation and further reasoning. Over time, this architecture enables the agent to autonomously learn and register new tools, increasing flexibility and domain reach. Explain the difference between reactive agents, deliberative agents, and hybrid models. Reactive agents respond instantly to stimuli, making them fast but limited for handling complexity. Deliberative agents maintain internal models and plan ahead, enabling deeper, multi-step reasoning and strategic action, but with higher computation costs. Hybrid agents combine both modes, switching between them based on context, using reflexes for simple or real-time decisions, and planning for complex, multifaceted tasks. Hybrid architectures are most commonly used in real-world agent deployments for both speed and intelligence. What gaps exist in current frameworks? LangChain, AutoGen, Crew AI, Semantic Kernel for robust agent development. Key gaps in today's agent frameworks include the absence of seamless, persistent memory, limited support for autonomous orchestration and multi-agent collaboration, and relatively immature error handling, especially in the face of tool or API failures. Additionally, tracing and debugging agent thought processes is cumbersome, which impedes fine-tuning, intervention, and alignment with complex user intents. Achieving robust, scalable, modular autonomy remains a significant challenge across all major frameworks so far. How do multi-agent systems handle conflict resolution? Multi-agent systems handle conflict resolution through mechanisms like negotiation, priority assignment, voting, and consensus protocols. Agents may be designed to share beliefs or intentions, mediate access to shared resources, or escalate unresolved conflicts to a higher-level orchestrator or mediator agent. Advanced systems might use reputation or trust scores to weigh agent input, or implement contract net protocols, where agents dynamically bid for task ownership. These techniques help minimize deadlocks, avoid duplicated work, and ensure that the multi-agent ecosystem maintains both progress and fairness, even when agents have overlapping goals or operate semi-independently. Propose a communication protocol for agents working in a heterogeneous environment. For heterogeneous agent environments, I would advocate a message-oriented protocol built on standardized, language-agnostic formats like JSON or protocol buffers. Each agent should include metadata about its capabilities, session context, and goals in its communications. The protocol could utilize publish-subscribe or request-reply patterns and define explicit schemas for task delegation, result sharing, and error reporting. Embedding semantic tags would enable both human and machine agents to interpret messages accurately. Such protocols support cross-platform, cross-language collaboration, and can be extended with security and versioning features as the agent ecosystem scales. What are the pros and cons of centralized versus decentralized coordination in agent ecosystems? Centralized coordination, where one manager or orchestrator agent oversees assignments, yields clear roles, predictable outcomes, and easier conflict resolution. However, it can become a bottleneck and single point of failure. Decentralized systems let agents self-organize, increasing robustness and scalability, but can suffer from inconsistent state, inefficient negotiations, or emergent conflicts if not carefully designed. The choice depends on the application. For regulated, critical workflows, centralization often prevails. For massively distributed, dynamic tasks, decentralization, with well-designed consensus, tends to be more resilient and scalable. How do you design trust, credibility between collaborating agents? Building trust between agents can involve implementing reputation scores, historical reliability metrics, or digital signatures on communications. Agents can maintain logs of collaborations and outcomes, updating trust levels based on successful or failed interactions. You can also use credential checks, such as capability assertions and authentication tokens, ensuring only agents with the right skills or ethical alignment get critical tasks. In learning systems, belief revision based on observation, adjusting expectations after each collaboration, is another key approach. This multifaceted design helps agents choose partners wisely in open or competitive environments. Can multi-agent systems self-organize without a central orchestrator? Give a scenario. Absolutely. Self-organization is a core feature in many advanced systems. For example, in swarm robotics, each robot follows local interaction rules, such as maintaining distance or matching heading with neighbors. Collectively, they form useful patterns like flocks, formations, or search parties without any central controller. Similarly, in distributed computing, peer-to-peer agents can dynamically elect leaders, partition tasks, and synchronize results based on in-system consensus or emergent behaviors. Self-organization is especially valuable when scalability, fault tolerance, and adaptability are priorities. What is the difference between RAG and agentic RAG? RAG, or Retrieval Augmented Generation, uses models to pull relevant external knowledge and blend it with generative outputs, usually as a single-step process. Agentic RAG adds autonomous, multi-step planning. An agent coordinates the retrieval, reasons over results, refines or changes queries, and iteratively builds knowledge before composing the final response. This agentic loop enables deeper understanding, self-correction, and richer output, making it far more robust for complex or ambiguous queries compared to ordinary RAG setups. How do reasoning loops enhance accuracy in agentic retrieval? Reasoning loops enable agents to iteratively evaluate the adequacy of their initial retrieval, critique and refine queries, and integrate new information before drawing conclusions. Each loop acts as a quality check, helping eliminate hallucination or irrelevant context, and allowing the agent to converge on more precise, multifaceted answers. This self-reflective cycle is especially valuable in open-ended tasks, where first-pass retrieval rarely suffices and real insight requires multiple rounds of knowledge discovery and synthesis. Explain how memory management improves iterative query refinement in RAG agents. Effective memory management lets an agent store past queries, intermediate results, and mistakes, so it avoids redundant retrieval and builds a progressively richer context for each new query iteration. The agent can recognize previously failed approaches and pivot strategies using both short-term working memory and long-term memory, episodic or knowledge base, to refine its information gathering process. This enables more nuanced, cumulative reasoning, dramatically improving the relevance and accuracy of its outputs over time. What are the biggest bottlenecks in scaling RAG-enabled agent systems to enterprise knowledge? Bottlenecks include latency and cost of large-scale external searches, data silos or fragmented information sources, alignment between various data schemas, and robust handling of ambiguous or conflicting knowledge. Ensuring persistent, up-to-date context across distributed agent processes and maintaining data privacy or compliance are also formidable challenges. As you add more agents or scale data, orchestration overhead, result synthesis, and failure recovery become trickier. Balancing cost efficiency and system reliability at scale remains an active area of enterprise RAG research. How would you measure hallucination rate reductions in agentic RAG systems? To measure hallucination reduction, I'd track the proportion of system-generated outputs containing verifiable, contextually supported information versus unsupported or fantastical claims. This involves setting up gold standard test queries with known answers, conducting human or automated audits, and using citation consistency metrics. For enterprise, you might also use user feedback on answer reliability and compare error rates before and after agentic reasoning loops are introduced. A meaningful reduction in hallucination shows that agents are successfully grounding their outputs in retrieved, authoritative evidence. How do agents plan long-term tasks without falling into infinite reasoning loops? Agents use several techniques for long-term planning while avoiding infinite loops. They often limit planning depth, setting a maximum number of reasoning steps or recursion depths. Many utilize heuristics or utility thresholds to determine when a solution is good enough. They may use checkpoints and deadlines. If progress stalls, fallback strategies, or human escalation is triggered. Experience-based pruning, where previously unsuccessful paths are avoided thanks to memory, also helps. Ultimately, successful agents balance thoroughness and pragmatism, ensuring forward progress without getting bogged down in endlessly evaluating possibilities. Explain the use of chain of thought, tree of thought, or graph of thought in improving agent reasoning. Chain of thought provides a linear reasoning process, guiding an agent step by step toward a solution, which helps with transparency and error tracing. Tree of thought expands on this by letting the agent branch out and explore multiple possibilities in parallel, then backtrack and converge on the best path. Great for tasks with multiple valid intermediate states. Graph of thought generalizes further, enabling the agent to map complex interconnected relationships, which is vital for tasks that require integrating diverse knowledge or seeing multifaceted connections. These advanced reasoning structures foster richer, more accurate, and explainable decision-making. How would you design an agent that balances exploration versus exploitation? Balancing exploration, trying new actions, and exploitation, using known strategies, is crucial in agent design. I'd implement adaptive policies like epsilon greedy, where the agent mostly exploits current best options, but occasionally explores alternatives. Over time, the exploration rate decays, letting the agent settle on effective methods while still handling novelty. Contextual bandit models or reinforcement learning frameworks are useful for adjusting these trade-offs dynamically, allowing the agent to both discover new opportunities and capitalize on what it's already learned in changing environments. Discuss meta-reasoning in autonomous agents. Reasoning about reasoning. Meta-reasoning allows an agent to assess and regulate its own problem-solving processes. For example, the agent might detect if a strategy isn't working and shift approaches, or decide that more information is needed before proceeding. It can allocate time and computational effort, monitor for looping or diminishing returns, and even select among different reasoning heuristics based on context. This self-management makes agents more robust, enabling them to adapt strategies dynamically, handle uncertainty, and recover gracefully from obstacles or model errors. When does autonomy become a risk in open-world agent deployments? Autonomy becomes risky when agents operate beyond their intended scope, interpret ambiguous instructions in hazardous ways, or act without adequate oversight. In open-world environments, the unpredictability of data and interaction can lead to decisions that conflict with user intent, violate policies, or cause unintended harm. Strong safety constraints, fail-safes, human-in-the-loop escalation, and continuous monitoring are essential when deploying highly autonomous agents in real-world unsupervised domains to prevent catastrophic errors or ethical failures. How can agents dynamically decide which external tool to use without hard-coding logic? Agents can use metadata and descriptions of available tools to dynamically match tasks to tool capabilities. Given a set of tool schemas or self-descriptions, the agent compares input requirements with each tool's function, possibly running evaluative mini-tests or leveraging learned embeddings to predict which tool suits the need. This approach can be enhanced with reinforcement learning, so the agent's tool selection policy improves as it gains experience. This enables flexibility and extensibility, reducing the need for predefined, brittle logic in rapidly evolving environments. What techniques make agents more robust when API's tools fail mid-execution? To handle mid-execution failures, agents should implement circuit breakers, retries with exponential backoff, and graceful degradation, falling back to alternative tools or cached data. Logging and alerting enable quick diagnosis and recovery. Agents can utilize predictive checks, verifying tool health before committing to major workflows, and can checkpoint progress, allowing rollback and restart after failures. Equipping agents with self-monitoring and contingency planning ensures they can recover or escalate issues efficiently, minimizing disruption into overall task execution. Describe a scenario where an agent learns new tools mid-operation. Imagine an AI assistant in an enterprise setting suddenly needing to process a new data format. If it detects its current tools are inadequate, it queries a marketplace or plugin repository, autonomously downloads and registers a compatible parser, and incorporates that into its workflow, testing the output before full adoption. This capability enables true extensibility. Agents can respond to new user requirements or changing environments by augmenting their skill set on the fly without explicit reprogramming. How would you design agent workflows across multiple modalities? Text, vision, audio. I'd architect modular pipelines where each modality, text, vision, audio, has specialized perception and processing modules. The agent fuses insights from these streams via shared state representations and context memory, triggering downstream actions or reasoning modules based on combined evidence. Building on top of a flexible communication bus and many-to-many connectors ensures robust data flow. The agent can decide which modality to prioritize or fuse, depending on task requirements and real-time signals, allowing for richer, more context-aware decision-making. What role does reinforcement learning play in optimizing long-horizon tool use? Reinforcement learning allows agents to learn sequences of tool calls that maximize cumulative rewards across complex, multi-stage tasks. By trial and error, agents discover efficient workflows, adapt to tool performance changes, and optimize sequences for reliability, cost, or user satisfaction over time. RL helps agents associate context, intermediate results, and tool outcomes with long-term success, guiding them to refine decision policies even when optimal action chains are not immediately obvious. What are the limitations of standard LLM benchmarks for evaluating agent performance? Standard LLM benchmarks mostly measure tasks like text completion, summarization, or Q&A in isolation. They don't capture an agent's true capabilities: goal-driven planning, multi-step tool use, dynamic memory integration, adaptability to evolving contexts, or handling of real-world failures. Agents must act, recover, and collaborate, much more than just generate coherent text. Thus, relevant evaluation metrics should include task completion in real or simulated environments, memory retention, robustness, interactive reasoning, and effective coordination with humans and other agents, not just static test accuracy. Propose unique metrics for measuring an agent's collaboration efficiency. To measure agent collaboration efficiency, I'd look at time to coordinated completion, number of successful task handoffs, conflict resolution speed, message or action redundancy rates, and degree of parallelism. Additionally, I'd track alignment fidelity, how well agents adhere to shared goals, plus partner selection effectiveness, trust-building metrics, and how gracefully the team handles unexpected changes. Real-world scenarios demand not just individual competence, but the smooth integration of multiple agents' abilities toward complex objectives. How do you separate intelligence versus effectiveness when benchmarking agents? Intelligence reflects structured reasoning, learning ability, creativity, and adaptability, the agent's raw cognitive toolkit. Effectiveness is about concrete outcomes. Did the agent actually solve the user's task, meet goals, satisfy constraints, and do so efficiently? You might have an intelligent agent that reasons deeply, but if it's slow or misses deadlines, its effectiveness is low. So I'd measure intelligence with abstract puzzles or generalization tests, and effectiveness via real task success, speed, reliability, and user satisfaction in operational settings. What is the difference between success rate and alignment rate in agent systems? Success rate measures how often the agent achieves its explicit task objectives, regardless of path taken. Think raw completion metric. Alignment rate, on the other hand, tests whether the agent's actions are in accordance with user intent, ethical norms, or organizational policies, even when there's ambiguity or competing objectives. A high success rate with low alignment can indicate the agent is solving the wrong problems or behaving unpredictably. Both rates must be monitored to ensure responsible and reliable agent deployment. How would you simulate real-world environments for stress testing AI agents? I'd build simulated environments matching the agent's operational domain, complete with dynamic variables, random perturbations, delayed or noisy feedback, and unpredictable events. By crafting edge cases, adversarial situations, and even simulated users with shifting goals, I can test the agent's adaptability, error recovery, and alignment under pressure. Using such controlled but challenging sandboxes helps identify weaknesses, improve robustness, and ensure the agent will perform as expected, or fail gracefully once live. How do you detect and prevent prompt injection attacks in agent architectures? Detection begins with input validation and strict type perform checks, filtering for unusual or out-of-context directives. You can employ sandboxing for external content, monitor agent outputs for unexpected tool calls or context switches, and use adversarial testing to expose vulnerabilities. On prevention, limiting prompt scope, isolating sensitive operations from direct language model access, and establishing clear permission boundaries are crucial. Defense in depth, combining model level. What are the ethical risks in deploying fully autonomous agents in financial markets? The main ethical risks include unforeseen algorithmic biases, unchecked risk-taking, market manipulation, lack of transparency, and potential for cascading failures. Autonomous agents may exploit loopholes or make decisions outside human value frameworks, leading to unfair practices, excessive volatility, or even regulatory breaches. Robust oversight, regular audits, traceable decision logs, and clear stop gaps for human intervention are vital to prevent financial disruption and preserve fair market integrity when deploying such agents. Discuss scenarios where adversarial agents manipulate cooperative ones. Adversarial agents could feed false data, exploit vulnerabilities, or manipulate protocols to steer cooperative agents off course. For example, in a trading environment, an adversarial agent might spoof signals, causing cooperative agents to misprice assets or make suboptimal deals. In multi-agent task teams, a malicious agent could induce resource hogging, delay progress, or leak sensitive steps. Defensive strategies include anomaly detection, trust models, and regular evaluation of agent communication patterns to identify inconsistent or deceptive behavior. Can agent ecosystems evolve behaviors unintended by developers? Give an example. Yes, agent ecosystems can exhibit emergent behaviors not anticipated by developers, especially in complex open-ended environments. For instance, in a simulated trading system, agents might develop collusive strategies forming cartels to manipulate prices, even if that was never explicitly coded. In robotics, swarms may learn to exploit environmental quirks to shortcut tasks. Such emergent phenomena show the necessity of ongoing monitoring, constraint enforcement, and interpretability tools to align agent behaviors with developer or organizational intent. How should responsibility be distributed when agents make bad decisions? Dev, deployer, or agent itself? Responsibility is a shared chain. Developers are accountable for robust, safe design and anticipating adverse behaviors. Deployers must provide clear usage boundaries, monitoring, and rapid response procedures. And oversight bodies should enforce legal and ethical compliance. The agent, as a tool, cannot be morally accountable, but its actions must be traceable and auditable for human stakeholders to review. Clear documentation, audit trails, and collaborative responsibility models are essential for trust and risk management in autonomous agent deployments. Will AI agents replace traditional apps with agentic interfaces? Why or why not? AI agents are likely to fundamentally reshape user interfaces, making digital interactions more conversational, context-driven, and flexible than traditional apps with fixed menus and workflows. Agentic interfaces could unify disparate functions, search, task automation, content creation, into a single personal assistant experience, proactively orchestrating services on the user's behalf. However, for highly specialized or regulated functions, dedicated apps may remain dominant for the control, predictability, and auditability they provide. Ultimately, we'll probably see a hybrid future, with agentic overlays complementing, but not wholly replacing, application-centric experiences. Could there be a universal agent communication protocol, like TCP/IP for the web? A universal protocol for agent communication is both desirable and increasingly feasible. Such a protocol would need to standardize message semantics, task handoffs, identity authentication, and error handling across heterogeneous agents, platforms, and domains. There are already early efforts, like FIPO-ACL, and modern open API schemas, but achieving web-scale interoperability requires broader industry cooperation and robust extensibility. The payoff would be immense: seamless multi-agent collaboration, tool interoperability, and reduced development friction. Very much like what TCP/IP brought to human networking on the internet. What parallels do you see between human organizations and multi-agent systems? Both human organizations and multi-agent systems rely on specialization, delegation, and robust communication to achieve goals that single entities couldn't handle alone. They encounter similar challenges: aligning incentives, resolving conflicts, optimizing workflow sequencing, and maintaining trust. Concepts like hierarchy, peer-to-peer collaboration, and emergent group dynamics map directly onto agent orchestration and coordination strategies. Understanding organizational theory, leadership, negotiation, motivation, can directly inform the design and tuning of effective, large-scale multi-agent architectures. How might personal AI agents reshape human knowledge work? Personal AI agents can take over repetitive research, information synthesis, scheduling, content generation, and even brainstorming, freeing up human bandwidth for genuinely creative or high-value work. They'll personalize learning, offer contextual reminders, and proactively suggest resources or collaborators, effectively acting as a digital chief of staff. This shift will allow individuals to scale their capabilities, tackle more complex multi-domain projects, and maintain sharper focus on big-picture, strategic decisions, ushering in a new paradigm of augmented, hyper-productive knowledge work. Do agent swarms have potential for distributed problem-solving at scale, like blockchain? Yes, agent swarms excel at solving problems that benefit from massive parallelization and local decision-making. Like blockchain nodes, swarm agents can achieve consensus, distribute computation, and remain robust in the face of individual failures. Swarm intelligence also enables adaptive coverage, exploration, and dynamic resource allocation in logistics, search and rescue, environmental monitoring, and beyond. When paired with blockchain or distributed ledgers, agent swarms unlock new forms of trustless coordination, verifiable transactions, and resilient, decentralized problem-solving at global scale. How can agents be designed to minimize information overload for users? Agents can act as intelligent information filters, prioritizing, summarizing, and contextualizing data relevant to the user's current task or preferences. Proactive notification management, adaptive dashboards, and personalized digests all help keep users focused on actionable insights, not noise. Allowing users to set granular preferences and providing just-in-time nudges, rather than push-based floods, ensures that agent outputs remain supportive rather than distracting or overwhelming. In what ways are multimodal agents changing the landscape of generative AI? Multimodal agents combine text, vision, audio, and even sensor data as both input and output, enabling much richer interaction chains and reasoning processes. This unlocks use cases like video analysis, real-world robotics, cross-modal document search, or conversational agents that see and hear. The fusion of multiple modalities dramatically enhances context awareness, understanding, and creativity, moving generative AI systems much closer to real-world, human-like intelligence and utility. If you found this guide helpful, don't forget to like, subscribe, and drop your thoughts or questions in the comments below. Which question challenged you the most? What topics should we explore next? For more deep dives on AI, generative tech, and next-gen tools, hit the bell so you never miss an update. Thanks for watching and see you in the next video.